18 is actually all about the atomic symbol, right? So you should know how to actually write an atomic symbol. Okay, typically you have this form where X is actually the latest symbol, Z is actually your proton number, A is actually your mass number. You can calculate your neutron number by using A subtract with your Z, okay? And then a few particles that you should know what it means, okay? Electrons and beta particles, they are actually the same, right? It's actually have the symbol E, okay, carry -1 charge, but doesn't have mass, okay? Positron looks basically identical to your electrons. The only thing that's different is actually it carries +1 charge. Okay. Alpha particle is your helium. Okay. Photon number 2, mass number 4. Gamma particle, okay, is actually a high energy radiation. It's actually coming from the combination of your electron and the positron. Electron and positron that give you 2 gamma radiation. Okay. If you have 1 electron and 1 positron, when they actually combine, they produce 2 gamma radiation. Okay. And the electron we're talking about is actually not a random electron we say that's surrounded by the nucleus, but the inner electrons. Okay. Generated from your nucleons. Okay. But it doesn't matter that much. The things that's important here is this. Okay, the nuclear equation. If you start from your X, defining X and T, okay, if you look into your photon number, okay, the left and right has to be the same. The mass number has to be the same. Okay, I want to give you some examples so that you can have a better idea what you should actually write. For example, if today I say, this part I feel like many people actually doesn't get it yet, okay, but you need to. Okay. If today I say there's actually a atom, okay, TH 9234 is undergo a beta decay. Okay, equation-wise, it will look like this. So this guy undergo a beta decay. You should know that the beta decay means actually you're going to have a beta particle, right? So that's actually an electron. Okay. When one thing undergo a beta decay, it's going to produce 1 electron on the product side. Okay, you need to make sure that you know everything. Every time you see a sentence say certain particles undergo a beta decay, equation-wise, that's actually what it means. You need to actually put your electron on the right-hand side, on the product side. Okay, so once you do this, then you need to actually apply the knowledge of these nuclear equations, right? The proton number need to be consistent. Here you have 90, here you have -1. That means the proton number of your new atom is called the proton number of 91. Okay? And then mass number is actually 234. That is 0. Therefore, you know you must have 234. Okay? So after that, then you start looking for the atoms that have the proton number of 91. 91, where's 91? This guy, right? 91. So you should put PA over there. Then you're going to get the correct species. So this will be actually the new atom. Then you have to go into the, then you have to provide an answer, okay, to that specific statement. Is that clear? Everybody follow this? It's very important. We're going to do some more practice today, okay? Second, if I say some particles actually undergo an alpha decay, right? You see this decay means actually things going to form on the product side, right? And then you should know that that is your alpha particle, right? Helium-24 is actually your particle. Now, you can actually start to write out your photon number, right? 92, 2. Therefore, this must be 90. Okay. 238, 4. This should be 234. Okay. So, photon number 90 will be your pH. Okay. So, this is the second example. Any questions so far? No? Okay, 2 more. Electron capture. Okay, so every time you see these things, capture is actually it got absorbed by certain atom. Okay, so if I say let's actually atom undergo an electron capture, that means actually the atom is going to attain 1 electron. Okay, so in this case, the gold atom undergo an electron capture. Then this should be actually the things you write out on the paper. Okay, so once you write these things out, then you know your photon number on the right-hand side should be 78. The mass number should be 195. Okay, so what's 78? Yeah, platinum, right? PT 78. Therefore, you know the answer you should put is this guy. All right. Very last one. Positron emission. Okay, when you see this word emission, that means it's equivalent to your decay. So write the things on the product side. Okay, if you write the positron, this is what it is, right? It carries +1 charge. Okay, carry 1 proton. Okay, then you can actually apply your nuclear rules. 6, 1, therefore you put 5 here. 11, 0, therefore put 11 here. Okay, so once you do that, then you check out your periodic table, then you find out you need to put boron in this atomic symbol. Okay, so I hope this example can make you feel more clear about what it means by the alpha decay, beta decay, positron emission. Okay, all these things you actually write these particles on the product side. Okay, but if you have an electron capture, okay, like capture means you need to write your electron on the reactant side. All right. Okay, so that's actually the first thing. The other important thing for chapter 18 is actually you want to predict whether a thing is actually stable or not. And if it's not stable, you undergo a radioactive decay. What kind of decay you are going to have? Okay, so if they are stable, if they are definitely stable, they must have the protons close to this few main number, right? 2A, 28, 82, 20, 50, 126. Okay, memorize it. Okay. But more importantly, how do you know it's actually unstable, right? The way you know it's actually unstable is actually you calculate the differences between your mass number and your real atomic mass. Okay, you get the atomic mass from your periodic table, you get the mass number from your atomic symbol. Okay, so if the difference is larger than 2, then it is not stable, you will undergo radioactive decay. Okay, the other criteria is actually if your proton number is actually larger than 83, then it's undergo a radioactive decay. Oh, yes. Which one? Yeah, that's for the special case. Live with it. Okay. I cannot go too far. I have to focus. Otherwise,
I have to focus, like, take care of the number 126, right?
yes, that's why I want you to actually memorize it. Special case, right? Okay, so what of the details you have? Okay, you use my table to do the prediction. Okay, so I group into like 4 different groups. Okay, 1 to 20, 20 to 40, 40 to 83, larger than 83. These are the 4 different groups, right? Each group has its own threshold, which is 1, 1.25, 1.5, 1.6. Okay. So if you calculate your neutron to proton ratio, okay, if it's actually larger than the threshold, then you're going to have the atom is going to undergo a beta decay, meaning you're going to produce electron on the product side. Okay. But if it's just smaller than the threshold, then you can either have the positron emission, okay, meaning you produce 1 positron on the product side, or you can have a electron capture, meaning you're going to get 1 electrons on the reactant side. Now it's either or. That means actually in your questions you only see 1 popping out. Okay, so it's either positron emission or electron capture. Okay. Okay, but if you have a photon number larger than 83, smaller than 80, larger than 83, but smaller than the threshold, then you're going to have alpha decay, meaning you're going to have a helium-24 appear on your product side. And not, yes. Okay, so the very last topic that we talk about for chapter 18 for midterm 3 is actually the decay, right? The decay kinetics. Only one equation, right? Natural of AT over A naught equals to negative KT. Okay. One thing you have to be careful about is that the AT or A naught. Okay, it can either be your number of particles or most of the particles. Okay, it can even be the concentration of your particles, or that's actually another example we'll go to later on. Okay, but it cannot be the mass of the particle. Okay, so that's very important concept you should have when you put on your AT and A naught. It cannot just be the mass of those species. Okay, and then one very classic dating approach is actually using the so-called isotope. Right? You measure the decay of certain species to know how old the subject is. Okay, so if you have a rock contains A and B particles, and B is actually the decay product of A. Okay, so the A will actually provide the number of A will provide the information of your AT. Okay, and then the A now will be calculated by summing up your A and B. Okay, so those are the things that we went through in the past couple of weeks. Okay, and that's actually all the things I think you should actually know for your midterm 3. All right. I hope this actually help you to refresh your memory, because we are going to go through all these questions now. Question number 1. The figure below represents the spontaneous reaction of H2 with O2. Okay, so the H2 is actually the shaded, O2 is actually the unshaded, to produce gas H2O. So this question, you actually give you these 2 things, okay? And then if you look at this 2, you want to know, is your delta S positive or negative? So you go from your reactant to the product side. So how do you count? Is the delta S positive or negative when you go from the left to the right? How do you know it's actually negative? The way you know is actually by counting what? The number of gas molecule, right? How many gas molecule you have for your reactant? 8, right? How many for your product? So your delta S is negative, right? It becomes smaller, right? Okay, but this question tells you this is actually what? Spontaneous reaction, okay? What does it mean? Every time you see spontaneous reaction, you should actually think of your delta what? Delta G. Delta G is negative. Okay? And then you know your delta G is delta H minus T delta S, right? Because you know your delta S is negative, right? So let me say your second term will be yes. So this term will be positive, right? So you also know what? You also know your delta G is negative, right? You know your delta G is negative. Then what is actually the sign of your delta H? It has to be negative, right? So once you figure this out, it's going to ask you, okay, under what conditions it is not going to be spontaneous? So your second term is actually positive, right? First term is actually negative. If your temperature is actually very low, then your delta G will equal to your delta H. They are going to have negative sign. Therefore, the things will become spontaneous. Okay? So you know, if T is very small, you are still going to have spontaneous reaction, right? How do you actually make it non-spontaneous? You have a very, very big T, right? Because when the T is actually very big, the second term dominates. Under the case, the delta G will become positive. Then things become non-spontaneous. So that is actually things that's trying to test you, right? It tells you it is non-spontaneous at high temperature, but it will be spontaneous at low temperature. Okay, the second question, find the temperature in K temperatures, which a reaction with delta H is 123 kilojoule per mole and delta S is 90 joule per K mole become spontaneous. Okay, so it gives you delta S, it gives you delta H. And for the temperature, we're going to see that this is going to change from non-spontaneous to spontaneous. Okay, so we'll see this. I feel like this is also a keyword that you probably actually want to recognize. Actually, something is going to become spontaneous under a certain temperature. Okay, what it means the certain temperature when you are at equilibrium. Okay, because you know if your delta G is negative, it's spontaneous. Positive is non-spontaneous, right? The turning point is actually at equilibrium. Okay, so the temperature at equilibrium will be the temperature this question is actually looking for. Okay, so temperature at equilibrium. Okay, since you know it's temperature at equilibrium, okay, delta G at equilibrium, you should have a clear idea that at equilibrium, delta G is going to equals to 0, and delta G is composed of delta H minus T delta S, right? And then after you know this, then you will come back and reread the information, then you'll realize that delta H is 123. Be careful about the unit. It's kilojoule per mole. You want to convert to joule. So multiply 1,000 minus temperature is actually things we are looking for. Times delta S is 90 joule per mole. sorry, per K. Okay, so this whole thing, when you add up, you need to equal to 0, right? So T is simply equals to 123,000 divided by 90. That's going to give you a temperature of 1,367 K. Okay, so this is actually how you solve the question number 2. Okay, so recap this. It asks you the temperature where the spontaneity is going to change, right? Therefore, it indicates you want to calculate temperature at equilibrium. Okay, you should know that at equilibrium, your delta G is going to equals to 0. Okay, and delta G is equals to delta H minus T delta S. Okay, you read the question, you know your delta H. Delta H typically given in kilojoules per mole. Make sure you actually convert into joule. Okay, delta S, just plug it in, and then you can calculate your temperature. Okay. Okay, which of the following has a positive value of delta S? So again, it's actually equation. It gives you this Pb solid plus Cl2G become PbCl2 solid. Which side has larger entropy? So if you calculate this, the delta S is positive or negative? It's negative, right? Why? Because you only have your gas molecule on your reactant side, right? So this is actually the one that's going to dictate the overall delta S, overall entropy. For the second one, you have of gas, 4 more on the product side, 5 more on your reactant side. Therefore, your delta S is also negative. Okay. The third one is only have the aqueous and solid, right? And aqueous have larger entropy than your solid. Okay. Therefore, you know the entropy on your product side is actually larger, right? Therefore, your delta S is going to be positive. Okay, so the answer will be just 3. Okay, next questions. Calculate the value of delta G naught in kilojoule for the combustion of 1 mole of butane with molar oxygen to form carbon dioxide and gas water. Okay, so translate a little bit. What does it mean? So it means actually your C4H10 plus O2 is going to give you CO2 plus H2O. Okay, so once you write this out, the first thing to do is actually make sure you have a balanced equation. Okay, because the coefficient matters, right? So if you look at this, since you have 4 carbon, right? So do that first. Okay, so once you have this, then the next thing you can do is actually H2, right? You multiply 5, then H will be balanced. Then you have A plus 5, 13 oxygen on the right. Okay. So do that, then you're going to have this balanced equation. And all of that is in the gas form. Okay. So to calculate your delta G naught, it's going to equals to your G naught formation of your product minus your G naught formation of your reactant, right? Of course, you want to actually taking care of your coefficient. Okay, so C1, C2, okay. So from the product side, you have CO2 and H2O. And then you look into this, delta G naught formation of your CO2 is negative 399, H2O is negative 225, right? So what you do is actually 4 times your negative 399 plus 5 times your negative 225. So let's actually the G naught formation of your product, okay, minus the G naught formation of your reactant. Okay, so for the C4H10 is negative 16, right? And the coefficient is actually 1. Okay, plus the delta G naught formation of your O2. Okay, So you will realize that there's actually no value for O2, right? Why imply to use actually the G0 formation of O2 is actually 0. Okay, so for this single atom molecules exist in their natural form, the delta G0 formation is always going to equal to 0. Okay, but if you don't know that, then it's true, because if it doesn't provide the delta G0 formation here, okay, it actually tells you it's 0. Okay, that's what it implies. Okay, that means actually this second term for your rectangle equals to 0. Okay. So if you do these calculations, you will be able to get a value of -2705. This will have unit of joules per mole. Okay. But these questions want to actually calculate in kilojoule. Okay, so will be 2.705 kilojoules per mole. Okay, so that's actually how you solve the question number 4. I guess it's actually not difficult. It's just like to know how you basic the concept of calculation the delta G naught, similar to how you calculate your delta H naught and delta S naught. Okay. Question number 5. The equilibrium constant for a reaction is certain number at 25 degrees C. What is the value of delta G naught at this temperature? Okay, so delta G naught is actually a keyword. Equilibrium constant is actually another, right? So the only equation that connect these two is that delta G naught is equals to negative RT natural log K. Okay, so it tells you your K is equals to 0.35. Temperature 25 degrees C is 298 K, right? So you just plug all these things in. Okay, so delta G naught equals to negative R. What's the R you should use? Yeah, make sure you know it's 8.314. T is 298. Natural log K is 0.35. Okay, once you do the calculation, then you will be able to get your delta G naught has a value of 2601 joule. Okay, which equals to 2.6 kilojoules per mole. Okay, so it's actually very straightforward, right? It's really testing whether you know the relationship between your delta G naught and K. Okay, so nothing special. Okay, so those are the 5 questions for the chapter 16. Then 17. Consider a Voltaic cell based on the half reactions. Identify the cathode and give the cell voltage under standard condition. Okay, what's the keyword here? Yes, Voltaic cell. Voltaic cell is equivalent to the galvanic cell, right? So what it means your E naught cell has to be positive, right? And if you look at two half reactions, they are both reduction reactions, right? Because it's always gain electrons, right? So let me actually to flip one of them, and after adding up, you have a positive value. Okay, so under that condition, the only one you can flip will be what? Your cobalt 2 plus, right? Therefore, you need to flip this. It become cobalt 2 plus 2 electrons. And then you're going to have your oxidation potential, which is going to equals to positive 0.28 volts, right? So once you do that, to calculate your E cell, basically you add up this value and that value, right? So your E cell is going to equals to 0.80 plus 0.28. They give you 1.08 volt. Okay. The next point is that who is actually your cathode? Cathode is what? Cathode, you can think about a G-rock, right? So G-rock is actually the half reaction who get electrons, right? Undergo reduction reactions, okay, serve as a strong oxidant. This can always happen at cathode, right? So who is actually getting electron? It's actually your Ag, right? So your silver plus, okay, getting the electron. Okay, so therefore you know your cathode has to be on the silver side. Okay, so that's actually how you solve this problem. Keywords: galvanic cell or Voltaic cell. Okay, that means actually inner cell has to be positive. Therefore, you can only flip one of the reaction. After you add up your E naught and the E naught ox, it has to be a positive value. Okay, and then after that, you should actually always remember low rod and G rod, so you can actually know who is actually your cathode, who is actually your anode. Okay. Number 7. Okay, it's actually about the notation, right? What is the balance equation for the galvanic cell reaction that corresponding to the shown notation below? Okay, so this is actually the notation that you're going to have in the questions, right? So when you look at this notation, you see the PT, right? Those PT is actually your electron. It doesn't involve in your reaction. Okay, so when you're trying to write out your reaction, just cross length out. Okay. And you look at this center 2 species, okay? So remember the show notation always have this ABC form, right? Meaning the first half is actually your anode, bridge, and cathode, right? For your anode, that means actually that's actually your LoRa, right? For your LoRa, you're going to have SN2 plus. They become SN3 plus. For your G-Rock, you're going to have your Br2 becoming your Br minus. Right? So first, the thing you do is actually translate the notation into a two-half reaction. Okay. So once you do that, then you start to balance the atom. Okay. For the top one, it's already balanced, right? It's just SN2 plus to SN3 plus. You have the same amount of SN. Yes. Oh, sorry, SN4 plus. My bad. Okay. But if you look at the bottom one, it's Br2 become Br minus, right? So you want to actually balance the atom over there first. Okay, so you put 2 over here. Okay, so that's now the second step you do, right? After you balance two-half reaction, then you balance your atom. Okay, and then you need to balance your charge, right? So for your LoRa, positive 2 on the left, positive 4 on the right, therefore you know you need to add 2 electrons. Okay, then you balance the charge of your LoRa. Then you want to do the same thing for your G-Rock, right? So Br2 become 2 Br minus, therefore you know you need to add 2 electron minus here. Okay, so once this is actually all set, then all you do is actually to add these 2 half reaction up. Okay, so 2 electron will cancel out. Then all you have is actually Sn2 plus Br2. They give you Sn4 plus 2 Br minus. Okay. So this portion is actually relatively easy because the electron got produced by your LoRa is actually the same as the electron got accepted by your G-Rod. Okay, so this is actually a simple case, but things can get more complicated, right? So if the electron got produced by your LoRa is not the same as electron for your G-Rod, then you actually multiply some factors. Okay, if that happens, then you're going to see the coefficient change in front of all your species that you have here. Okay. So let's actually how you solve question number 7. Question number 8. The standard cell potential for a dry cell battery is 1.56 volt. What is actually the standard free energy change for this specific cell? What is actually the keyword? Battery, yeah. Okay, so a few keywords, highlight this. What is this? Yeah. Translate, okay, delta G. What else information do you have? Yes, very good. What is this? E. There you go. Okay, so this actually delta G naught, right? So here apparently it's actually equation. The equation that you need to use to connect these two, right? So your delta G naught and E naught cell. Okay, so this two term is actually connected with this, right? Delta G naught is equal to negative N times F times your E naught cell. Okay. All right, so apparently, I hope everybody see that this actually turn into calculate, right? Delta G naught, right? Now, in order to actually know your delta G naught, you need to know a few things. One is your E naught cell. One is actually your N. F is just a constant, right? F is just barely constant. Okay. Do you know your E naught cell? The E naught cell is what? 1.56, right? That means actually once you figure out your N, then you're done, right? Okay, so what is actually N though? In order to know the N, you actually need to look into the equation and find out who is actually your LoRa, who is actually your G-Rock. Okay, so zinc, what's the oxidation number of zinc solid? 0, right? How about MM? 4 plus. Okay, you need to get faster, okay? N, sorry, this NH4 plus. -3, good. This? -3. This? +3, right? This? +2. Okay, so this doesn't really matter, right? So if you look at this goes from here to here. And then zinc goes from here to here. Right? Those are the pairs that undergo the change of octet number, right? So who is actually your LoRa? LoRa is actually the one who has oxidation number goes up, right? Therefore, you know it will be the Zn solid become Zn2 plus. Okay. G-Rock will be your MnO2 become Mn2O3. Okay, so now you can determine the okay, so this 2 MmO2 become Mn2O3. Okay. So on the top is already +2, right? So you know to balance it, you add in 2 electrons. Okay, at the bottom, we know originally you have +4. This become +3, right? You have 2 of them. Therefore, there's also this actually 1 electron. Actually, going from +4 to +3, there's actually 1 electron reduction, but because of 2, therefore this is also 2 electron transfer. Okay. So if you look at this 2, then you realize that it's actually LoRa give you out 2 electrons. Your Gra is going to consume 2 electrons. Therefore, the number of electron got transferred is actually 2, right? Therefore, you put 2 for your N. Okay, so this one will tells you the N equals 2. Okay, so once you do that, okay, your F is 96458. Okay, once you do that calculation, you're going to get your delta G now is going to equals to 300.95 joule. Okay, but you want to 300950. It's not 300. 300950 joule, which is going to give you 301 kilojoules. Okay, so that will be actually the answer. Okay. So that's how you do the question number 8. Number 9, balance the following equation in basic solution using the lowest possible integer and give the coefficient of water. Okay, so keyword basic solution, coefficient of water. Okay. Since it's actually a basic solution, right? If you are missing H, you use H2O. You're missing O, you use 2 equivalent of OH minus. Okay. Right. Oxidation number of manganese. Plus 7. Good. Br minus -1. MMO2 plus 4. BrO3 minus plus 5. Okay, so Laura, who is actually your Laura? Right, so Br minus becoming BrO3 minus. G-Rock, MnO4 minus becoming MnO2. Okay, so that's first step, right? Second step, balance the atom. Br is the same. Oxygen is actually the one that's missing, right? So you have 3 oxygen on the right. Therefore, into add in what? Add in your OH minus, right? How many OH minus? 6. Okay, so 6 OH minus. Okay, then into actually balance your H, right? How many water into add in? 3 H2O, right? Then the Laura will be balanced. Okay, look at the bottom. Manganese is balanced, right? You have 2 extra oxygen on the left. Therefore, into add in 4 OH minus. Okay, and then add in 2 H2O on the left. Then your balance will 0. Okay. And after this, then you need to actually start to balance your charge, right? So on the left for your Laura, -6, -1, make it -7 on the left. On the right, you only have -1, right? So into add in 6 electrons. Okay. Look at the bottom. On the left, it's actually -1. On the right, it's -4. Therefore, you may add in 3 electrons. And the electrons will be balanced for both your Laura and 0. All right. And then you want to make sure if the electron generated by your Laura is the same as the electron got accepted by your G-Rock, right? So you know your Laura generates 6, G-Rock only accept 3, right? Therefore, you want to multiply your G-Rock by 2 before you adding up. Okay. So once you do that, you're going to have 6 OH minus plus Br minus plus 4 H2O plus 2 MnO4 plus 6 electrons. That's going to produce BrO3 minus plus 3H2O plus 6 electron plus 2. This actually better, right? Under plus 2 MnO2 plus 8 OH minus. Okay, so once you have this, then you know 6 electrons will cancel out. 3 H2O cancel out with this, so you have 1 H2O remain. 6 OH minus, so this one become 2. So the final equation will be Br minus plus H2O plus 2 MnO4. That give you BrO3 minus plus 2 MnO2 plus 2 OH minus. So the coefficient in front of your water will simply equals to 1. Number 10. How many grains of chromium metal can be played out when a constant current of Am is passing through an aqueous solution containing chromium 3 plus for 40 minutes? Okay, what is the keyword here? Yes, electroplating, right? Plate it out is actually a keyword. Okay, so equation to use. Grain is going to equals to m times second divided by n times your Faraday constant times your molecular weight. Okay. Do you know the m? Am, right? Do you know the time in second? You have 40 minutes times 60, right? Do you know number of electron got transferred? How do you know it's 3? Yeah, because it says 3 plus, right? So it's 3. Faraday constant. What's the molecular weight? Molecular weight of what? What is actual molecular weight you should use? Yeah, what's the product? Do you see this? Yes. Chromium metal, right? So you check out if you are able to check out the molecular weight of chromium. Okay. They will give you a number of 51.996. Okay, so once you do the calculation, you're going to get a value of 3.45 gram. Okay, so a few things that I feel like you guys can get confused is that how many electrons? Okay, so electrons, like, I feel like everyone have good response for that, right? The second section is what is actually your product? Okay, every time you see a question like this, really think about what is your product. Okay. Question number 11. The half-life of beta decay of certain things is 28.8 years. A milk sample found to contain 10.3 ppm. How many years will pass before that species concentration drop to 1 ppm? Okay, what is the keyword here? Half-life is actually a good keyword to memorize. Every time you see this half-life, write down your natural log. AT over A naught equals to negative K times T. Okay. So once you have this, then you start to look into the equations. Okay. It says half-life of this species is 28.8 years, right? So last time we said every time you see this sentence, you want to use this one to calculate your what? Your K, right? Because you know half-life means actually your natural log 1/2 is going to equals to negative K times 28.8 years, right? Therefore, you can calculate your K is going to equals to 0.0241 per year. Okay, so that's actually the first step you do, right? You get your K. Okay. But it says, how long will these things, how many years will pass, right? That means actually you want to know your T, okay? Right now you know your K already. That means actually, can you actually define your AT and A0? right? So what is actually your AT based on the description? $10.3 is your AT. Why? AT is current, right? AT is current. So who is actually your current? 1.0 ppm is your current, right? You start from 10.3 ppm. So let's say you're A0, right? So all you need to do is just do this, natural log 1 over 10.3 equals to negative 0.0241 times your t, and solve for your t. When you do that, your t is going to equals to 96.8 years. Okay, so from the response, we can see that what is the confusing part? Distinguishing who is actually AT, who is actually A0, right? So what would be actually a good rule of thumb to predict who is actually AT, who is actually A0? Decay always from a large number to a small number, right? So we look at this 10 and 1. Okay, even you don't have any knowledge about whatsoever, put 10 in front. Okay, so of course, if you have common sense, right? If you have good understanding of the decay process, okay, then you should tell, okay, you want to go to 1 ppm, right? So that will be actually your current. Okay, therefore you know the 10 will be actually where you started. Okay, very last one. Okay. A freshly prepared sample chromium 243 undergo 3312 disintegrations per second. After a certain time, the activity of the sample declined to 2755 per second. Asks you for the half-life, right? What are the keyword here? Half-life again, right? Therefore, you know, natural log AT over A0 equals to negative K times T. After you write out this, what other information that you know? Okay, AT, A0, what else? Time, very good. Okay, time is the easy one, right? What's the time? 6 years, right? What's your AT? Good, 2755. A0 will be 3312. Okay. I want you to pay attention to this, okay? The unit. Do you know what this means? Disintegration per second. Okay. The only thing that you want to pay attention to that is that you want to make sure it is not max. Okay. As long as the value it is not max, then you can use it. Okay. So this specific one is actually talking about the activity. Okay. Activity depending on how many molecules that you have. So it's actually a different way of telling you how many molecules that you have in the sample. Okay, even though we don't really know what it means, right? It's actually a specific terminology. Okay, but the important thing is that you want to make sure that is not the max. Okay, then all the other things is okay. Then go from big to small is actually the good trend to use. Does that make sense? Yeah, so do that, please. Okay, so by doing this, what can you get? Natural log 2755 over 3312 equals to negative K times 6. Apparently, you can get what? Your K, right? So the K is going to equals to 0.0307 years. Okay. But they are not actually asking for the K, right? It's asking for your T half, okay? T half means natural log 1/2 equals to negative K 0.0307 times your T half, right? You're still using the same equation, but you should know that the T half means actually your natural log term is actually natural log 1/2, right? Therefore, your T half will equals to natural log 1/2 divided by 0.0307. That's going to give you a value of 22.6 years. Okay, so this is actually how you solve a question like this. Okay,